Assalamualaikum. My name is Muhammad Firdaus Zulkifli. My metric number was 1B225101888. So today I will present about the project objective, system modeling and analysis. First one, we have the three objectives for this project. First one is to derive the mathematical model of fourth order RLC electrical circuit. And number two was to perform system analysis using transfer function, frequency domain, and step space time domain. And the last one, to determine system stabilize and analyze transit response parameter via MATLAB simulation. So our group choose a question number 4. So before we start the project, we need to know the component we use and the value of the component. So for the first component was resistor. R1, R2, R3 was used at 10, 20, and 30. For the inductor, L1 and L2 was the same value, was 33. And capacitor for C1 and C2 was the same value, was 4.7. Let's look at the KCL at node A, which is located at the left junction of the circuit according of Kirchhoff current law. The sum of all current leaving the node must equal 0. So for the equation was VA over L1 plus R1 plus VA minus VI over L2 plus VA minus VC plus 1 over C1 equal to 0. So for the next one, by grouping the state variable VA and VC together, we obtain a simple algebra equation ready to solve. As shown right below, VA bracket 1 over L1 plus R1 plus 1 over L2 plus C and close the bracket minus C1 multiply VC equal to 1 over L2. So for the next one, let us shift our focus to the right side of the circuit, especially KCL at node C. In a similar manner, the current equation for the three branches paths connection at node C is formula as VC minus VA over 1 C1 plus VC minus V1 over R2 plus VC over R3 plus 1 over C2 equal to 0. And the next one, you get the minus C1 VA plus VC, open the bracket, C1 plus 1 over R2 plus C2 over R3 multiply C2 plus 1, close the bracket, and you get the answer 1 over R2. So for the last one was VC2 equal to VC, open the bracket, 1 over C2 over R3 plus 1 C2, close the bracket, equal to 1 over R3 C2 plus 1. So that's all for me.
Assalamualaikum warahmatullahi wabarakatuh. My name is Amirul Ahmad bin Razali and my matrix number is B122510183. And now I want to explain about part A1 final numerical transfer function. As you can see, this picture is tugasan part A1 transfer function. The mathematical model transformation manual equation from nodal analysis are computed using MATLAB. Then the SS2TF function is used for exact conversion to ensure high computational accuracy. Next is part A1 final numerical transfer function key observation for group G4. First is for the system, the highest power in the denominator is S power 4 due to the 4 energy storing elements, which is 2 indicator and 2 capacitor in the circuit. Next is non-minimum phase system. The negative sign in the numerator indicates the presence of a positive zero, which causes an initial negative undershoot in the time response. And last is high complexity, reflects highly interactive and fast dynamic exchange between the R, L, and C components.
Assalamualaikum. My name is Iman Suhairi bin Muhammad Khairul Saleh, number matric B122510170. For my part, I'm going to explain about part A for unit step response analysis. From the common window MATLAB, we can see the rise time is equal to 6.25 microsecond, which is very fast. And the peak time is 24.52 microseconds. Setting time is 0.68 microsecond, which is stable below 1 millisecond. And then percentage overshoot, we got 40.21%. Peak voltage is 0.696 voltage. And lastly is steady state value 0.23 voltage. This slide shows about unit step response using modern state space. As you can see here, there is a marking point 1 and point 2 in the graph. Point 1 is an initial negative undershoot, which is structural negative dip, confirming a right half place, positive 0, indicating a non-minimum phase system. And the point 2 is underdamped transient oscillation. It's a rapid transient remain caused by continuous electrical and magnetic energy exchange between the L and C component. For the point 3, which is peak overshoot at 40.21%, it's a maximum peak voltage of 0.696 volts achieved very quickly at 24.52 microsecond. For point 4, steady state convergence. Final convergence and stability achieved at 0.23 voltage within 0.68 millisecond, matching theoretical DC circuit calculation.
Assalamualaikum and hi, my name is Nourish Ilham binti Muhammad Faizal. My metric number is B122510182. So let's look at part A3, which presents the pole zero map and stability analysis. As shown in image, the right side displays the exact mathematical value of the system poles and zero from the MATLAB command window. The key takeaway here is the stability of the system. If you look at the pools, every single one of them has a negative real part, such as negative 2.8174 and negative 0.1480. When mapped onto the complex plane on the left, all, all poles lie entirely on the left-hand side of the imaginary axis. In control system theory, this proves that our system is completely stable. Okay, now let's we move on to the bullet points and data slide, where we define our state space representation for group G4. First, we selected four state variables. Number one, X1 T representing the voltage across capacitor 1. Number two, X2 T representing the voltage across capacitor 2. Number three, X3 representing the current through inductor 1. And number four, X4 T representing the current through inductor 2. For our system setup, the input UT is the input voltage source VIT and our target output YT is defined by voltage across capacitor 2, which corresponds directly to X2T. Using the standard state space equation shown here, we derive our numerical system metric. Metric A is a 4 times 4 metric that captures the system internal physical connection and energy exchange. Vector B is a 4 times 1 and column vector showing how the input source drive our system state. Vector C acts as the abstraction row defined as 0100, which targets our second state variable. Lastly, metric D is a zero metric, indicating no direct feedthrough from input to output. Part B, which cover the state space unit step response simulation. For our time domain simulation setup, we initialize this state space model in MATLAB using the SS command. We apply a 1.0 V unit step input and execute the simulation via the step command. The resulting waveform is displayed in the plot on the left. Based on this, we extract the calculate metric alignment for group G4. The rise time Tr is incredibly fast at 6.25 microseconds. The settling time Ts takes about 0.68 milliseconds. We observe a noticeable oscillation with a percentage overshoot of 40.21%. This results in a peak voltage Ymax of 0.696 V before the system dampens out and stabilizes. Continuing with part B2 on this slide, we focus on the validation and mathematical equivalent of our work. On the right, you can see the continuous time transfer function model SYS_TF generated for tugasan part A1, where we compare its response to our state space model. The output curve display identical other depth characteristic as the frequency domain model. The exact overlap of these response parameters thoroughly validate the physical consistency of both methodologies. Therefore, our validation verdict is that both the time domain state space and frequency domain transfer function equations are mathematically isomorphic. This confirms that our complete model verification is successful. Thank you.
Comparison, transfer function, and state space. First, domain. Frequency domains, state space is time domain. Second, perspective. Transfer function, black box, model focused really on input-output relationship. State space, internal, dynamic, model focus energy storage element. Last one is benefit. Easier to analyze stability, pole and zero, and steady and state error. State space is provide a complete view of internal state variable, capacitor voltage, and inductor current. Conclusion and recommendation. First, project achievement. Successfully derived the fourth mathematical model use nodal analysis and state space formulation for group 4. Second, verify the strict mathematical equivalence between the frequency domain and time domain system model. Key technical finding. First, the circuit is confirmed to be stable since all system pole lie on the left half plane. Second, the system is non-minimum pace exhibiting a temporary negative understood due the positive zero. Last one is dynamic response is underdamped, showing ultra-fast transition in the microsecond range.